Hello again. This is Matt 2134 coming to you from the College YouTube page, and this lecture is derivative of exponential functions. Make sure you're an active learner as you view these videos. So let's recall that an exponential function grows very, very fast, and so it looks like the curve seen here. Recall also that the derivative is the slope of the tangent line. So if I were to draw the tangent line here, the slope is very close to 0. If I draw the tangent line here, the slope is a positive number, and it gets to be a bigger and bigger positive number at these other places where I would be drawing the tangent line. So I can make a qualitative conclusion here that the derivative of an exponential function y equal b to the x, where b is bigger than 1, is going to grow very fast, and it's going to get bigger and bigger as x gets bigger and bigger. And for reasons that will become clear later, we're going to talk about the derivative of e to the x first. And you remember that e is an irrational number that is a little bit bigger than 2.71. So we're going to show that the derivative of e to the x is in fact e to the x. It's the only function whose derivative is equal to itself. To do this, we're going to go all the way back to the definition of the derivative. So y equals f of x equal e to the x. So this is the limit definition of the derivative. So the limit as h goes to 0 of f of x plus h minus f of x all by h. When I use y equals f of x equal e to the x, I get this as e to the x plus h minus e to the x over h, the limit of this as h goes to 0. But I can factor e to the x out of this numerator, because e to the x times e to the h is e to the x plus h, and e to the x times minus 1 is minus e to the x. So that is certainly true. But this limit is as h goes to 0, and there is no h in e to the x. It is like a constant relative to this limit. And remember that we can pull constants through the limit sign. That's exactly what we did here. We pulled e to the x through. So now we are faced with a question of, so what is this limit as a number? Well, we're going to talk about this many times in this course, but today we're going to look at just the tabular method of picking values that get ever closer. H is getting ever closer to 0 from the right. And we evaluate this expression, and we see that this gets closer and closer to 1. For the limit to exist, it has to be the same from both ways, so we're going to let x get closer and closer to 0 from the left, and again we're getting closer and closer to 1. So you see this is 1, and that means the derivative is 1 times e to the x, at least based on this argument. And again, we'll revisit this later many times. You might ask yourself, what happens if the base is not e? So let's just say, what happens if y is equal to f of x is equal to b to the x, where b is a number bigger than 1, and for example, it could be 2 or 3. Well, the same calculation using the definition of the derivative, we get that f prime of x is equal to b to the x factors out, because b does not depend on h, and we're faced with evaluating this limit. Now, very soon, I'm going to show you that that number is equal to the natural logarithm of b. But now we have another result for exponential functions. If y equals f of x is equal to b to the x, then f prime of x is equal to b to the x times the natural logarithm of b. Notice that if I let y equal b to the x, and b is e, the natural logarithm of e is 1. And so this is consistent with what we did. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.